Hi, I'm DJ Ware. Welcome to my channel. And today on the Cyber Gizmo, we're going to be doing a comparison between Gluster versus NFS. NFS, as you know, is a traditional protocol used in NAS systems, and so I think it's appropriate to compare the older technology with the newer, and let's just see what some of the differences might be. So before we do that, let's take a look at the setup that we'll be using today. So the test hardware is an Odroid HC1 by hard kernel, and that is a Samsung Exynos 5422. That has 4 Cortex-A15 processors running at 2.1 gigahertz, and it has 4 Cortex-A7 processors running at 1.4 gigahertz. And so that is a big little architecture, and you probably recognize that as being a cell phone. So for the purposes of this, you can consider it an 8-core processor with 4 of them running fast and 4 of them running slower. There's 2 gigabytes of LPDDR3 RAM, and there is a SATA 3 connector that's included with the board and the heatsink, which is the black metal shroud that the motherboard is mounted to. It also includes a gigabit Ethernet, and the hard drive that we'll be using for the tests on our systems is the Hitachi TravelStar 7K1000, which is a 2.5-inch 7200 RPM 1 terabyte disk drive. The software that we're going to be testing with is the Ubuntu server for ARM, and that's the 1804.2 LTS version. The kernel is supplied by Odroid, and that's 4.14.127-164, and that's compiled for ARM v7L. The GlusterFS server version is the latest at the time of this video, and that's 6.3. The NFS server version is the NFS kernel server, and that is 1.3.4-2.1 for ARM-F. Wow, what a mouthful! I don't know if they could make that probably a little simpler with their versions, but for some reason that's the way they do it. We'll be using iozone to conduct the performance tests, and we'll be using the latest version of that. That's version 3.487, and that's targeted for Linux ARMs. So we want to keep this all on the same platform for our tests, both on the server and on the clients. The setup for the GlusterFS, we're going to be using a distributed replica volume, and we'll be using 3 replicas out of a total of 6 hard drives attached to 6 different machines. The command used to create those is shown below. And you'll probably notice that if you look at the command, it says volume create drep1. drep1 is the name of the volume. Replica is the number of volumes to set aside for replication. And then we'll be using the TCP/IP protocol for the transport. You can also use RDMA. And then the list of machines and the location of the bricks to be used to create the volume. So how do you notice that there isn't a way to really define distributed replica, so how is that done? If you have a multiple that's greater than 1, if you have a multiple of machines that's greater than the replicas, then the system assumes that you're trying to create a distributed replica. So what does that mean? So distributed means that we'll be pushing files out across all of the servers in kind of a balanced mode, and then the replicas are pushed out to the rest of to at least 3 of those servers in order to create the ability to do a quick restore in the event of a failure. The reason you use 3, you can use 2, but you may run into a situation where you have a split brain condition that you have to recover from. And a split brain occurs because the system can't figure out which of the 2 replicas is the one that you really want to use to recover the file with. And so we use 3 to give it a 3rd vote to break the tie. The options at the bottom are default. I did not tune this for iozone for 2 reasons. One, I feel that would be cheating. And the second reason is that you normally do your tuning for the workload that you're going to be using. And again, if I did that, I would be tuning it for iozone, and so I didn't want to do that. That might introduce bias into the results. And the third reason is I wanted you to be able to have a way to replicate these results for yourself using similar hardware. The NFS setup is also an Odroid HC1. It also uses the Hitachi 7K1000 disk drive. The export file, we're going to be using async mode, and I'll explain the reason why for that later. All the tests are conducted on the same machine as a client, and the mounts are done as we do the test. In other words, I don't mount the NFS. I don't mount the NFS partition until I'm ready to use it, and I don't mount the Gluster brick until I'm ready to use that as well. Some explanation for the iozone tests. So the initial write is test writing to a new file. The rewrite tests writing to a file that already exists, because there's some performance gains there in that you don't have to create the system overhead like inode tables and all that and entering the directory. Read tests are simply performance of the read of an existing file. Read allows us to get a measurement on how much of that the system is caching. So it gives us some idea of performance if the operating system is performing caching on recently read data. Reverse read tests reading the file backwards from the back to the front. You might think that's a little strange, but there are applications that do this, and so we want to measure those as well. A stride read basically does a 4K read, then it does a seek for 200 kilobytes, does another 4K byte read, and then it does another seek, and so on in repetition. And the reason for this test is that this simulates when an application is storing structures within the file. Random retests just simply read at random locations within the file. It just changes the location randomly and then performs a read. Mixed workload allows for overlapping read and writes within the same test, and this would also occur at random locations within the file. Again, there's applications that do that as well. Random write tests the performance of writing to random locations within the file, and also p-write, which tests writing to a file descriptor at a given offset. And there are a number of applications that do that, particularly with imaging. Some of the more advanced imaging that has a lot of metadata in front, p-reads are done to read out the binary part of it after the metadata has been processed. And same with p-write, it allows you to advance to be able to store a binary part into a file which has quite a bit of metadata. Fwrite tests writing a new file using the fwrite function. And so this would be a buffered I/O, and it would also be handling blocked I/O. This would be common in streams. And also with fread, same thing, except it's reading from an existing file, and it would also be simulating a stream I/O because it's handling buffers and also blocked. So let's take a look at the first performance test. I did this as kind of a control, so we would get an idea when we were looking at the performance what the Odroid is actually able to do if we're conducting an iozone test directly on the hardware. So there is no network involved. There aren't any protocols involved. This is strictly reading the disk directly off of the file system. And we can see that, and this is typical with most of the systems, is that the read performance is quite a bit higher than the write performance with spinning Rust, and that's just the nature of the beast. We'll talk more about some of the results later when we get to that part. And the NFS trials, it's pretty consistent with a few exceptions, and again, we'll talk about those as well. You'll notice in my tests with, this is conducted again using the Odroid test, this is well below the network bandwidth, and so there is some overhead that the NFS protocol is adding to the system. But in all, it's still pretty good. You might notice a declining random write, and we'll talk about that when we get to that part as well. For Gluster, the writes are pretty consistent with the performance of the direct file system, and then you'll notice that there is some scaling that's going on as we add users. So, and we'll talk again about that when we get to the performance part of this, but you'll see that Gluster scales with the load. The cost for this, for an Odroid HC1 is about $50, and 7 of that, you would add $7 more onto that to buy the power supply. There is a 5-volt 6-amp version of the power supply if you feel that you need that. Although in my experience, the 4-amp is fine for a 2.5-inch hard drive. The Samsung EVO Plus 32 gig was used for the operating system, so that's the boot disk. And then again, the Hitachi costs about $50, and that is new. You can buy refurbished ones for a lot less, but I would really recommend against that because you're really buying a drive that is worn out and probably won't last very long. Ethernet cable, about $4. So about $120 each for the systems, and a total in this test of about $717. So let's talk about some of the results. The direct drive performance was slower than I expected for the reverse read, and it should be a little bit higher than this, and the reason why I say I'm a little disappointed with it. But in all, based on the interface that the Odroid uses, it's quite good. And the interface it uses is it has a J micro USB to SATA interface, and so it's really using the USB as for the bandwidth and reading from the SATA. And normally in your home PCs or whatever uses SATA to do that. So, PCIe. To do that, so you gain a little bit higher performance with the drives in a PC versus the Odroid. But for $50, not bad. The read and writes are as expected, and then the performance, as you saw in the graph, drops as we add more users, and that's due to contention for the heads and the drive, and that's to be expected, really. And the reason why we don't we don't do too much direct drive without having it on a RAID is in order to spread. We want to spread that contention. NFS results: random read performance declined as the user load increased, and that was a bit odd, to be quite honest. I suppose that's because of the NFS overhead in writes, because it is going to try to, it can't obviously cache that because it's randomly writing to locations. So it can't do any kind of performance enhancement. So as the load went up, the performance dropped. The rest of the tests were good and pretty consistent. There was one instance on P-write where the performance fell off as the count hit 5. I am using asynchronous writes on this run of NFS. Normally, I set up my servers with synchronous, but if you do that on the Odroid, your performance will drop drastically. And when I had sync turned on, my writes were about 18 megabytes per second, and that's not very stellar. But I think that's just the overhead of all of the protocol layers that it's going through in order to accomplish that write. In the Gluster results, the write and rewrite were consistent with the single disk drive performance. So if you look back in the video with the single drive performance, you'll notice that Gluster's results are pretty consistent. And the way that the distributed replica works, we're not speeding up writes at all. We're getting what we're getting from the drive that's in use. And the other thing to remember is that in Gluster, a write does not complete until the replicas are completed as well. So when you're issuing a write, it's actually writing 4 times in order to put the file down, once on the primary and then 3 times for the replica. In our case, anyway. The read performance is consistent with what I've seen in the past for Gluster, and it scales with load. Of course, the single user workload is not ideal, and this climbed up pretty nicely until I reached 5, and then it capped out the network. and that's great. If you this is 5 simultaneous users, and so that would translate to about 50, yeah, about 50 users. The way we would do a rule of thumb, that would be about 50 users on that particular Gluster network would be able to be handled, and that's quite impressive for $700. The file size, of course, is a small file workload, and that's not ideal for Gluster. There is some performance tuning you can do for that, so if your workload is going to be small files, you can do performance tuning, which will help that. But I think all in all, it's a good test for an average use. I personally use my Gluster for my a home directory on all my machines so that I have a consistent set of files when I log into the various machines on my network. And so some final thoughts. An enterprise Gluster installation in the real world would start at $30,000. But of course, it would scale much larger than my tiny example here. So the price is proportional to the amount of storage that you would be getting from it. And then they can grow up to, as we've talked about before, petabytes in size. They scale way, way up. You can build a Gluster cluster for about half the $700 amount because we're using the replica or actually doubling the price that we would need in order to build a Gluster cluster. But if you can live without as much replication, you can reduce it to 2, but you do take a risk that you may have a split brain, or you could just do a distributed cluster and risk losing everything if one of the servers falls because there will not be any recovery. Also, it's a good way to learn how to use Gluster. And the other thing to remember is that Ceph also runs on this hardware, so you can use it to learn both. Although Ceph will take 2 extra servers in order to stand it up. Just because that's the architecture of Ceph. I didn't test Samba or CIFS. I don't run Windows and don't have any intention to ever running Windows. The other bonus you get here is that and when you have 6 machines, you actually get 24 high-speed cores and 24 low-speed cores. So that's pretty impressive. And if you use something like a Beowulf cluster or a MPI cluster, you'd be able to utilize those even with Gluster running. There's plenty of performance and plenty of horsepower left on those machines to be able to actually run workloads on them. In the real world, in the Xeon world, the best you can do right now is about 28 cores per CPU, and of course you would need 2 of those in order to match the number of cores that you would get with the Odroid. And that would come at a cost of about $8,700 each as of the time of this video. It's quite pricey, and that's just for the CPU alone. That doesn't include the motherboard or the case or the power supply or the network cards or any of the other infrastructure that you would need to stand that up. So that's something to think about. $700 is not bad compared to that. So will I be replacing my ZFS RAID NAS? No. I do use Gluster, but I don't use it for a NAS. And that's simply because that involves small workloads, small file workloads, and Gluster isn't good at that. But if I was storing a lot of video, which I probably will be in the future, then I might consider that and do that for storing some of the videos here. So I hope you enjoyed today's talk and a look at the performance of Gluster versus NFS. And if you did, please like and subscribe and leave a comment if you're so inclined. Hope to see you again soon, and bye for now.